Hi, this is a short video on springs. So this video will include the relationship between the force of springs and its change in length, and the spring potential and energy involved when we stretch and compress a spring. Okay, so let's begin with a spring, and we'll say that this is its relaxed state, or when the change in length, delta x, is equal to 0. And we'll also denote that the right direction is positive in all of our scenarios here. Okay, so let's stretch the spring. And when we stretch it, we're stretching it to the right. So we have a displacement going to the right, a change in length of delta x, which is positive. So we also need to have a pulling force that goes into this positive direction. But Newton's third law states that if you have one force, you must have another one. So forces come in pairs, and this other force must be equal and opposite. So this is the force exerted by the spring. And since the pull force was going to the right, this means this force is going to the left, or in the negative direction. Okay, so let's consider a compressed spring now. So we can see that compared to the relaxed state, the change in length is going into the negative direction. So delta x was negative. Alright, so now we have a pushing force to compress a spring, let's say. But forces coming in pairs, so this means that the spring would actually be pushing in the opposite direction of this pushing force. And so the force of the spring in this case is going in the positive direction. So to sum it all up, we can use Hooke's law, and this denotes that the force vector of the spring is equal to the change in length multiplied by negative k, the spring constant. Let's quickly go through the variables here. So first we have the force vector. So this is the force of the spring, so it's not to be confused with the force that's being exerted onto it, the force by the spring. Okay, so next we have, well, not a variable, but it's the negative sign here in front of the k. So this may be confusing at first, but all this means is that the direction of the force exerted by the spring is always opposite to the change in length, as we could see before, where if you have a compressed spring, we're pushing it in, right? So this means the change in length would be going in the negative direction, but the force exerted by the spring would be going in the opposite direction, in the positive direction. Okay, next up we have K. So this is probably something we're not familiar with unless we've dealt with springs before. So K is the spring constant in newtons per meter, and it signifies that the spring force is proportional to the change in length. Lastly, we have the change in length, noted by delta x. So change in length is in meters, and make sure you actually sub in the change in length when using this formula, and not the length of the spring itself. So careful not to confuse it with that. Okay, so with all these vectors, sometimes it's a little bit confusing. So we're just concerned with the magnitude of our force and change in displacement. So more often than not, we're gonna write our Hooke's law as just F equals to K delta X. So if you want to present this on a graph where you have the magnitude of the force versus its magnitude of change in length, then we're just going to end up with a linear graph. And the gradient here is just going to be K. Alright, so let's start looking at the spring potential energy, or I'll just abbreviate this to SPE in this video. So SPE is simply depicted by the area under the force versus change in length graph. So here we can have another force versus delta x graph. It's a linear graph, so we just have this diagonal straight line. And the area under here is our SPE, so the shaded area in yellow. And to find this area, well, we can just use geometry, right? So we just find the area of the triangle. So the height of the triangle is force, base of the triangle is delta x, so we just have half times F delta x as our area. So recall that the force of the spring is actually just k delta x from Hooke's law. So this means when you sub this in, your area or your SPE is just equal to half k delta x squared. Alright, so additional note. So this formula just doesn't come from nowhere. For a little bit of magic, you can use a bit of integration here. And what happens is that when you integrate the force, which is a function of the change in length, and you have it your upper limit as x1, lower limit as 0, what happens is that, well, first of all, you need to sub in k delta x as instead of f from Hooke's law. So once you integrate, you'll get something like this. And subbing in delta x with x1, you'll get your SPE formula. So x1 is just the magnitude of delta x, just so we can keep this definite integral. So that last part's pretty supplementary, and you often don't need to remember that, but it's good to know where all of this comes from, and it's just not from thin air. Alright, so this concludes this video on springs involving the force, change in length, and SPE. Thanks.